我原想整个春晚全用机器人，是不是很大的？整个春晚。
I originally thought about making the entire Spring Festival Gala performed only by robots. I wondered if it would be something huge. Imagine presenting the whole gala this year entirely with robots. The idea was that every performance on the stage would be done by robots. When I first invited the actors, I told all of them that they would just stand below the stage as audience members. Do you think they were excited about that? All the actors, Shuntung, Qianqi, and everyone else, were very upset. I even wanted Nana, and they were all quite frustrated. From the very beginning, the idea had been to use only robots, and we had been preparing for that possibility the whole time. At that time, the technical team asked me, what if we provide 20 robots? Or maybe 25? They suggested dividing them into 2 groups, or even 3 groups, and asked whether that would work. I said it would be very simple. Every day we would rehearse twice, with 3 groups of robots rotating on stage. I would rehearse once at dawn and once again at dusk, 2 rehearsals every day. If we rehearsed for 10 days, that would be 20 rehearsals in total, and I could just select the best version. If everything were performed by robots, the whole Spring Festival Gala would be solved. 10 days would be enough. In the 10 days before that, we could create the programs using AI, input the data into the robots, and as long as they could provide about 25 robots, we could complete an entire edition of the gala. The employees thought the idea was incredible, but the challenge was enormous. Nothing could go wrong. However, in the end I still gave up the idea. Do you know why? I studied a huge number of robot performance shows. For example, robots performing kung fu. And especially in the past few days I watched robots doing comedy sketches, crosstalk, singing, dancing, everything. I studied them carefully, over and over again, but I just couldn't make up my mind. Actually, during last year's Spring Festival Gala, I already wanted robots to perform a stunt called breaking a stone on the chest. But in the end we didn't do it. Do you know what the biggest problem is? Of course, it's a psychological issue. Simply put, the biggest problem is excitement. A Spring Festival Gala needs excitement and laughter, but the comedic moments can't be guaranteed. When a robot performs martial arts or executes a perfect 360-degree spin like an acrobatic stunt, the scene is so shocking and impressive that the humor disappears. The whole show becomes full of spectacle, but without laughter. Even foreigners would be scared. If a robot performs crosstalk and keeps throwing punchlines one after another to make you laugh, before you even start laughing you're already shouting. That's amazing. That's incredible. The sense of shock overwhelms the humor. The better the robots perform, the more impressive it becomes, but the harder it is to highlight comedy. Even before filming, I knew the comedic timing wouldn't work. A robot simply cannot replace a master comedian like Uncle Ben Sean. The second problem is expression. More than half of a robot's expression is lost. Every robot looks almost the same. Their eyes don't change, their faces barely move. They all seem as if they were carved from the same mold. They don't cry, they don't laugh. The whole gala would become monotonous and lifeless. After more than a month of internal struggle, I made a major decision. At that point, every robot had already been designed based on real actors, and even the hosts would have been robots. But after more than a month, I gave up the idea. The first person I called was Uncle Yu. I told him that I was abandoning the plan of using only robots. He was shocked and said that was impossible because he had already fully immersed himself in the idea of a robot Spring Festival Gala. He was even thinking about taking over future shows. He sent a robot to try to convince me. The robot told me I didn't need to say anything, that my concern was simply that the robot's face looked stiff. Then it demonstrated by turning its head 360 degrees and said it could keep spinning for 24 hours non-stop. In the end, it ran out of battery. After that I told the actors we would still need them. Chun Xiaoqun joked that he had practiced clapping for a month for nothing and now needed something spicy to eat. When everyone realized the gala would not be entirely performed by robots, they all felt a bit disappointed. I told Yu Yunpeng that he would still have to sit below the stage and clap, and he joked that he actually supported the idea of an all-robot show. I told Leopard that the robots would only replace them when announcing dish names, and he joked that maybe he didn't even want to perform anymore. Of course it was all jokes, but in the end both the robots and the people seemed a little disappointed. When I saw everyone's reaction, I felt sad as well. I really did. But eventually I still chose to abandon the idea. In the end, the Spring Festival Gala became a lesson. For a world that seeks harmony between humans and machines, replacing everything with robots could actually be destructive, showing that robots are capable of everything. So what? You lose life. You erase human characters. Which matters more? So I am still learning. I am learning how to think as a director working with robots. This is my regret, but perhaps it is also a moment of clarity, understanding that robots ultimately exist to serve human beings.
The 2026 Spring Festival Gala, the Yushu 5 BOD robots kung fu performance shocked the entire robotics industry. In just 2 years, robot motion control and what many people call the little brain side of robotics have already been pushed to an extreme level. Before this, I had already made 2 videos, one about the many different ways to use the Yushu robot dog, and another about the technology behind Yushu's robot fighting competition, which are on another channel, and I'm going to bring over to this one. In this video, we're going to keep digging deeper into the more than 20 algorithms behind this year's Spring Festival Gala performance. How were these amazing movements trained? Was there really a human remotely controlling everything? Can small companies and independent developers reproduce the same effect as the show? Besides performing on stage, what else can these robots actually do? And beyond that, we're also going to talk about the 3 major technical trends that are currently growing wildly in embodied intelligence, along with 3 long-standing weaknesses in the robotics industry that this year's performance once again exposed. Let's start with the first question. Were there or were there not humans controlling the robots behind the scenes? Was there a motion capture actor assigned behind every robot? Or was there some operator piloting everything backstage like an Avatar or Pacific Rim? The answer is no, because the effect shown in the performance has already gone far beyond the level of every full-body teleoperation system that currently exists for humanoid robots. First, let's look at some of the best teleoperation systems available. Twist, open source by Z1GA's team at Stanford, can perform real-time, full-body teleoperation of Yushu robots using motion capture. Then came an improved version, Twist 2, which replaced motion capture with a cheaper VR headset. GMT, published by the Beijing Institute of Technology, together with a national and local co-built Humanoid Robot Innovation Center, can use motion capture, a VR headset, or even video input to control a robot and make it perform difficult full-body movements. That classic viral T-pose gear-shifting moment from a while back was done with this system. Westlake University also introduced an excellent motion capture system called JE. For example, in a performance by the Fudan School of Management, the human performer danced backstage while the Yushu robot reproduced everything in real time on stage. This system is simple and direct. All you need is a human performer and a very good 5G connection. A friend of mine has a company that works as a Yushu distributor and specializes in exactly this kind of performance, and almost every show they do becomes a huge hit. These teleoperation systems usually use 2 models, one large and one small. The larger model acts like a kind of pre-trained motion intuition, making the movements fluid and realistic. The smaller model is there to follow the motion capture performer's actions. That's why in the videos released using these systems, even when a robot falls, it still tries to stabilize itself, resist disturbances, finally adjust its posture, and at the same time imitate human movement as closely as possible. There's a certain calmness to it all, almost as if it were natural. But these methods have 2 major flaws. The first is latency, which is high. If that weren't the case, the operator wouldn't sometimes get caught off guard by the very robot he was controlling. The second is that they can't perform very large amplitude movements. If a human makes a big leap, the robot can only do a restrained version of it, almost like saying, "That's as far as I go." So how are these incredible movements trained? The answer is by collecting human data, converting that data into the robot's joint trajectories, training in a simulation environment with imitation learning and reinforcement learning, and finally deploying the result onto the real robot. This is what's called motion tracking, a deep intelligence journey that blends art and technology, simulation and reality, carbon-based life, and silicon-based bodies. The first step is collecting human data, and for that, those full-body teleoperation systems we just mentioned are enough. The problem is that high-quality human data is extremely expensive. And if on top of that you invite microcontrol masters like me and Badao, then it gets even more expensive. But the data collected from humans can't be used directly to train the robot because the difference between physical joints is simply too great. That's why the second step is needed: redirection or retargeting. Basically, you take the coordinates of the human body, solve them inversely to find the corresponding joint angles of the robot, and then make the robot execute the same movement. Only then do you get what's called the reference motion, which can actually be used for training. Zaewon Jay's team at Stanford proposed an extremely powerful retargeting method called GMR. It takes the same segment of human data and smoothly transfers it to several different robots from Yushu, Axel Evolution, Foulier, and others. Even though these robots have completely different bodies, the dance ends up looking almost identical and without any awkwardness. This redirection can be done either with motion capture data, like in the RGMT system mentioned earlier, or with pure vision, identifying the human pose directly from camera images and then mapping it onto the robot. The third step is training reinforcement learning algorithms in a simulation environment. Back in 2018, Berkeley proposed a groundbreaking project called Deep Mimic. With just a set of motion capture data as reference, it was already possible to train a character to perform a whole sequence of continuous movements. Imagine how impressive that was inside a game. A stick figure could execute precise kicks, fluid attacks, varied motions, all of them smooth every time. Reinforcement learning practically injects a soul into those movements. It can even allow creatures like a Tyrannosaurus to learn how to use its tail to balance its center of gravity while walking, or let a dragon adjust its gait when disturbed by outside forces, making those cyber creatures look genuinely alive and fluid. Later, that same Berkeley team proposed AMP, where another AI evaluates the gait generated by the main AI. Through adversarial learning, the system is pressured into producing movements that feel even more realistic and human. The biggest challenge in simulation training lies in the physics engine, the rendering engine, and the 3D assets. That is exactly one of NVIDIA's major moats. In China, only a few companies and labs such as Songyin Technology, Guanglun Intelligence, and the Shanghai Artificial Intelligence Laboratory are trying to follow this path because building it from scratch is an enormous amount of work, almost like rewriting an entire video game engine. The fourth step is deploying the algorithms trained in simulation onto the real robot, the so-called sim-to-real process. The example of the Yushu robot dog walking on a yoga ball was done exactly this way. It was first trained in NVIDIA's simulation environment and only afterward transferred to the real robot. For that to work, the yoga ball in the virtual environment has to match the real one as closely as possible in size, elasticity, and material. My own small open source robot, the OpenMaca Mini, was also first trained in an open source simulation environment and only then deployed onto the real machine. In the same way, the virtual world and the physical world have to be made as similar as possible, narrowing the gap between simulation and reality so that the algorithm trained virtually can adapt to the real world. Looking again now at that platform jump scene in the Spring Festival Gala, I really do admire Yushu's engineering department. Those four steps together make up the workflow of imitation, learning, motion tracking, and deployment for humanoid robots. Even though every stage looks full of challenges, the truth is that today there are already several relatively mature open source solutions, and both small companies and independent developers can reproduce them at low cost. The first of these is Beyond Mimic, open sourced by a Berkeley researcher. It's basically a ready-to-use codebase that established best practices for training robots to perform almost any kind of movement. After training, even if you kick the robot while it's dancing, it can stand right back up and keep the music going, keep the dance going. Even a broke student like me, buying a small robot for around 20,000 yuan, can use GM2 with retargeting and Beyond Mimic for secondary development and finish a graduation project in a single afternoon. The second open source solution is Omni Retarget for Yushu robots, published by Amazon's F2 team led by Yang Luji. Enhanced jumps, flips, obstacle crossing, and even box carrying shown in demonstrations can all be achieved with this algorithm. The retargeting and data augmentation in that paper were done in a very clever way. During the Spring Festival period, Yang Luji also published new work in which the robot receives a depth camera for vision, achieving an effect very similar to the show. The robot decides on its own whether to climb stairs or scale a higher platform without needing pre-programmed motions or a fixed environment. The paper's homepage even includes a simulation game demo in which you use the WASD keys to control the robot as it approaches platforms from different angles and watch how it chooses on its own how to get over the obstacle. The third open source solution is Humax, released by the Hong Kong University of Science and Technology together with the Shanghai AI Lab. With just a human video, it becomes possible to train a corresponding object interaction skill. In testing, objects like basketballs and water jugs are covered with reflective markers, and the capture system tells the robot their 3D coordinates. You can observe several curious phenomena. When a human waves a boxing glove or pretends to throw a ball, the robot shows an almost instinctive stress reaction, trying to respond to or compete with the human. The data generation, simulated interaction, skill imitation learning paradigm, and model distillation mechanism in that paper are all extremely ingenious. And it's worth noting that all three of these solutions were published only within the last year. When that handkerchief throwing performance happened at last year's festival, they didn't even exist yet. Today, embodied intelligence is splitting into three major trends that are growing in a somewhat wild way. The first is the one we just talked about, motion tracking, the branch focused on imitating impressive human movements, mainly used in humanoid robot performances. The second is the VLA branch, which imitates humans doing work and is applied mainly to robotic arms and dexterous hands. The third is the world model branch, which tries to go straight to the point and generate both the physical world and the actions in one shot. Examples include OpenAI's Sora, Tesla's FSD, and future models of this type. SenseTime also released a world model called Kaiwu, capable of generating a video of a robotic arm turning a faucet with water pressure, flow, gravity, collisions, and contact all being simulated directly by the model itself. Antlingbo's world model is also extremely impressive. With the W, A, S, and D keys, you can move through a world generated in real time, and with only a nearly complete initial image, it can create an almost infinite game world. As for the second trend, VLA, it has advanced rapidly in recent years. Behind that Spring Festival Gala skit featuring Shen Tang, Mary, and Galaxy's general-purpose robot are large vision language action models such as Aloha, Pi 0, Pi 0.5, and Smart VLA. Robotic hands can now pick nuts from shelves, lift grilled sausages, and fold clothes. These movements may seem simple, but they show that there is now not only the cerebellum responsible for locomotion control, a brain for manipulating objects is also emerging. At the beginning of 2026, Xiaomi, Ant, Lingbo, and the Damo Academy all open source their own large VLA models, which means that even ordinary developers can already start experimenting with them. For example, I built a system where a robot picks up a crayfish, dips it in sauce, and drops it into a pot, all in one complete sequence. The process begins with teleoperation to record 100 camera videos and trajectory datasets. Then the VLA imitation learning algorithm is trained, and the robot learns to perform the whole sequence by itself. In another project I did, I first used teleoperation with 2 robotic arms to collect data, then trained the VLA algorithm, and the result was a 2-armed robot that cooperates with itself, even toasting with its own hands, organizing a desk, and putting objects away. Even if you replace the pen with a brand new one, it can still identify it and place it in the basket. After that, it can wipe the desk and hold a mechanical pencil, creating a minimalist, interactive art installation based on embodied intelligence. You stretch out your hand, it stretches out its hand too. You pull back, it pulls back too. This 3D printed robotic arm setup costs just a little over 1,000 yuan and can be assembled in 2 hours. Then, by using the open source Lubrock framework and following the very beginner-friendly tutorial documents from colleagues at Tongji University, you can also run the entire VLA imitation learning pipeline and make the robot perform all kinds of polished and interesting tasks. And this fluid sequence of actions can be very long. For example, Qianxun Intelligence's system for folding clothes can work continuously, even in a 2-4-hour live stream. It was one of the things that impressed me most at the 2025 World Artificial Intelligence Conference. Another case was Zibian Liang's robot making aromatic sachets, performing a long sequence of picking things up, filling them, pulling the string, attaching Velcro, and finally handing the finished product to me, all with refined two-arm coordination. Recently, that company also open-sourced its giant VLA model and is running an embodied intelligence hackathon called Project Juliang to look for creative applications, with very generous prizes. By following the same tutorial documentation, anyone can train effects like cloth folding pretty easily. But despite how fast the technology is advancing, this year's Spring Festival Gala robots still exposed 3 major long-standing weaknesses in the industry. The first is that their ability to interact with objects is still very poor. The box of magic props had to be handed to the robot. It couldn't pick it up by itself. The nunchaku performance looked impressive, but in reality, the nunchaku was fixed to the robot's left hand, just like last year when a handkerchief had to be pulled by a string. Compared to simply performing motions, what we really need are works like Human X, where robots genuinely interact with real-world objects. The second major limitation is that, in practice, robots are still almost blind. On the Yushu robots used in the festival, you could clearly see a 128 Line 3D hemispherical LiDAR unit mounted on their heads during rehearsals. With that, they build maps through SLAM to locate obstacles, something similar to autonomous driving based on high-definition maps. Tencent's intelligent mobility team had even previously built a guide dog using Yushu robots based on the same principle to help visually impaired people. But at the end of the day, that is still map recognition, not actual vision. If the world changes, the robot gets lost. This method does not solve the classic problem of allowing a robot to climb any kind of stair freely. Professor Zhuang Zinan of Tsinghua University has presented 3 very interesting works using depth cameras to tackle exactly this problem. In one of them, the robot directly uses the built-in depth camera in its head to autonomously observe platforms, stairs, and steep ramps. When you guide the robot to the base of the stairs, it analyzes the depth map itself, decides where it can step, and lifts its foot on its own. In another case, similar to Parker, the system also uses a depth camera to stabilize the head. They even strapped 2 wooden rods to the robot's neck. It looked ugly and improvised, but it worked. In another demonstration, again using a built-in depth camera, the robot performs parkour and clears obstacles. Maybe the effect isn't as visually polished as the Spring Festival Gala version, but the landing posture still looks very stylish. There is also another project in which a robot dog uses an external Intel RealSense camera and behaves almost like a Special Forces soldier, squeezing through narrow gaps, climbing high platforms, and crossing ditches. The third major limitation is that dexterous hands still aren't very useful for practical everyday applications. Right now, demonstrations involving these hands are extremely repetitive. At almost every expo, you see the same things over and over again: rock, paper, scissors, piano playing, remote control gloves, prosthetics for disabled users. Always the same old 3 tricks. There are still very few applications that ordinary people would actually use in daily life. And in fact, as Wang Xinxin said, the robot brain is still not general. The industry still needs more time. Right now, the entire embodied intelligence sector is waiting for its own GPT moment. If you enjoyed the video, leave a like, subscribe to the channel for more videos like this, and I'll see you in the next one.